It's my pleasure to introduce Belinda. She's from Columbia University, and she has a lot of very nice works on diffusions and sampling in general. And today she will talk about variational principles for mirror descent and mirror Langevin dynamics. We're looking forward to it.
Hi, thank you very much, and thanks a lot to the organizers for this amazing program and for having me. So yes, this is the title of the work that I'm going to present, and to be honest, it's actually not very self-contained in terms of motivation, and my goal today is actually to convince all of you that stochastic optimal control has a lot of interesting perspectives to offer in terms of diffusion models and sampling in general, and sampling using first order methods. So this is joint work with Raj, Max Rubinsky, and Francis Bach. Okay, so my working assumption is that people here are not super familiar with optimal control. So I'm from computer science, so there are a lot of RL people. So I guess people are not so much working in that vein over here. So I'll just spend time on some preliminaries, and as a result, the talk will be not very vigorous, because otherwise I would just spend an hour talking about optimal. Okay, so what is optimal control basically? And very high level, we have in the context of diffusion, some generic diffusion process with diffusion coefficients, and we can control this process by adding a drift term. And the reason that we don't want to actually control the diffusion coefficient is there are multiple reasons. Some of them mathematical, and one of them is, you probably should be quite intuitive, which is that, well, if you affect your noise process, then suddenly you're going to have problems with your filtration quite likely, and you don't want to deal with the issues of measurability via your control. And the other one is sort of moral, which is that, well, optimal control tends to have very physical applications and physical motivations. And, you know, when you have a controlled process, you want to think of your noise as exogenous. So you have your action, which is deterministic, and you're basically being affected by some noise that is given to you by nature, and you don't want a model where you can actually control the nature-given noise. That would be kind of weird. Okay, so the actual problem is that we have some process, and we want to, via our action, our control, to minimize some sort of cost, or in the stochastic case, then expected cost, which looks something like this. An expectation that consists of a control cost that will be some usually well-behaved kind of function. It's convex, or at least smooth in both arguments, over your finite time horizon, and then some terminal cost function depending not on any control, but just on the terminal state that you attained. And usually the control will be from some nice parametric class. In general, our conditions aren't our control, because it is basically an additive drift term, or all of your regular properties that you want for your effective yesterday. We don't want to have like super polynomial growth or whatever, because then our control diffusion is not going to be very good. Okay, so why do we want to think about control? And my answer is that it offers a unified way of thinking about both the forward and backward processes of a diffusion model. So, well, we can think of sampling via an optimal control. So if we want to have some desired distribution at a finite terminal time, so without loss of generality like 10 equals 1, starting with some Gaussian, what is the most efficient, which we'll get to what that means, what is the most efficient way of transforming that Gaussian into our desired potentially very complex, we're just saying continuous for anything else, sort of desired terminal distribution? What is the most efficient way of doing that? That is the forward process. And backwards, we can do variational inference by considering some suitable tests of this parametric controls, where we have, say, a sample from your terminal time, and variational inference will proceed by going backwards, minimizing the elbow, for example. And of course, we have as usual with inference and this flexibility trade-off. So the more expressive your class of controls, the better your inference will be most likely, but that's the test as well. It's going to be complicated and harder. And I'll just touch upon this very briefly later on, but there's many connections to other topics of interest in machine learning, such as dynamic optimal transport. And it should not be hard to see why. Okay, so what this talk will focus on is the difference between optimal control and gradient-based methods. So algorithmically, at a high level, what are they saying? So, I mean, we all know very well by now that gradient flow or Langevin diffusion are just doing steepest descent with or without some added Gaussian noise, and you just keep doing that step by step until you've converged, or approximately, whatever approximately means to you. On the other hand, stochastic optimal control, where we're talking continuous or discrete time, we want to minimize our control costs over some finite time horizon, and then with our terminal costs tacked on at the end. So already we see that these should be like inherently very different problems. And more specifically, I mean, what is gradient flow, gradient descent? I mean, it's a greedy algorithm. You're just literally doing steepest descent. You don't care about what you did before. You don't care about what you're going to do next. You just steepest descent, step by step, until there's no more left to descend. And on the other hand, control is akin to dynamic programming. So you have some optimality criteria, and you basically have to, for example, in the discrete setting, you have to fill out your table where you're going to be and how much that costs you step by step. And again, one is asymptotic, you converge asymptotically, and the other is you are completely done by your specified finite horizons. And the other thing, which, I mean, this is not subtle, but it's a big difference, is that with the gradient flow, you don't know where you're going to end up. You just go until there's nowhere else to go. But for the control problem, you absolutely do know where you want to go. It's captured in a terminal cost. And that's going to be baked into your problem. So of course the question is, okay, are these just like hopelessly like apples and oranges? When can we ever compare them? And I mean, intuitively, you should think that no, most of the time they should not be comparable, because, for example, if we think about NP-hard problems, there are many greedy approximation algorithms, and they have, in general, they have constant approximation factor error. So on the other hand, for example, you can almost technically solve the problem with numerical error. In many cases, using like fully polynomial time approximation schemes. And that is dynamic programming that will get you almost exactly the optimal solution. So in the case that there are easy problem instances where your greedy solution and your optimal solution line up, sorry, your solution values line up, do these solutions themselves actually line up? And there's no reason to think that they should. Just because you're greedy attains something that is close to optimal, it doesn't mean that the structure of the solution resembles the actual optimal solution. Okay, so why should we try to think of them as similar? So minimizing control cost is actually, well, it's just you're trying to be efficient in some way. There's some criterion. And on the other hand, gradient descent, gradient flow, Langevin is doing steepest descent, which by nature is efficient because you can obviously descend in other directions that are kind of extraneous. And moreover, what we know from machine learning, obviously, is that gradient descent is kind of magical. It's not just that the algorithm is efficient in being greedy, but the solutions found are pretty remarkable. There's often implicit regularization in number senses. The path traversed by iterates is actually often very surprisingly short, even though there's no like hard-baked constraint for it to be that way. Often the norms of the solutions found are quite small. For example, in logistic regression, we often find so-called minimum number solutions that correspond to the max margin. And then, as I'm sure many of you know from machine learning literature in the past few years, there's a lot of attention on so-called lazy training, or in the case of a two-layer very wide, almost infinite neural network, the weights move very, very well in optimization. So there's some kind of parsimony going on, and parsimony is important. And on the other hand, optimal control, maybe we can be more efficient, but at what cost, right? Well, it's something that a solution that is obtained via dynamic programming. So the structure is going to be probably much more complicated, where you have to know where you currently are within your time horizon and where you want to be at the very end. Whereas for Langevin diffusion, well, it's just green and flow. It's easy. You just go until you're converged in the sampling or optimization sense. Okay, so more concretely, and in terms of the actual control problems I'll be talking about, we have a cost to go function for our, and that is composed of a running cost from some intermediate time to your endpoint and a terminal cost. And this choice of terminal cost will become clear in a moment. And as person doing time horizon will also generally be 0 to 1. And the value function is simply the infimum of the cost to go function for all state variable x and time t over our desired class of controls. And the optimal control is the one within our class that attains the value function for all times t. For all states x and time t. And our goal is, of course, just to minimize this total cost, which is sum over control cost and our total cost. Okay, and here are some structural results. So with the cost function, terminal cost function, as we've specified, which is what the minimum total cost looks like, expectation that depends on our terminal cost function at our terminal state, conditional on where we started. The optimal control is negative gradient of the value function. And okay, gradient has appeared. I think that could be kind of interesting. And the optimal control diffusion process has a transition density that can be related to the transition density of the uncontrolled process. And then you can think of this as being reweighted by a relative likelihood given by the so kind of one of the keys of control is that the value function solves any value function for control problem will solve an HGB equation. So here's a PDE with the terminal condition, and you can actually kind of back of the envelope get the HGB equation just from doing a Taylor expansion. And okay, this would be kind of nice, but on the other hand, like, okay, we have optimal control is the negative gradient of the value function. So it's gradient descent, but of course the value function encodes our terminal criterion and where we are at time t. So it's some sort of gradient descent, but okay, well, like what is the value function itself in terms of the other quantities in the problem? And for this particular problem, we do a long transform. It was popularized by Fleming back in the early 70s. We actually have a rewriting of the HJB equation, and Feynman-Cox formula tells us that this actually is the solution of the optimal control. Okay, so what do we care? So optimal control gives us many ways of thinking about sampling, and one of them is via the Schrodinger bridge problem. So the Schrodinger bridge problem, the most basic sense of it, there are many variants of it, is that we want a drift that will take some particles with a distribution at time zero to some desired target distribution. Same, that's absolutely continuous with respect to the three-dimensional Gaussian. At time one, while minimizing the full control effort. Okay. All right, this is a very old problem, almost 100 years old. And one nice result is that this sort of a variational result is that for any control, the control cost will be lower bounded by the KL divergence between our target density and the starting Gaussian. And the optimal control is the so-called Bellman drift, which looks like this. So one thing to note here is that okay, optimal control sounds great. You can do this thing that minimizes cost with respect to our criterion. But actually, like, do you ever want to implement this? And the answer is no, most likely not, because I mean, if you look at this thing and you write it out, first of all, you get a 1 over 1 minus t term. It's kind of like a Brownian bridge. So that thing is not necessarily going to be very well behaved as you approach the terminal time. And moreover, you have a ratio of expectations, right? And how are you going to approximate this thing? Well, you have to approximate this with samples, and your empirical average will require samples that, yes, they can be polynomial in all your parameters, but I mean, it's very different from sampling with a standard diffusion process where, well, at every time step, you just have something that's nonlinear, but otherwise quite simple. Like if you want to sample with the Fulmer drift, you basically have to have some large but polynomial size neural network at every time point, just to approximate the Fulmer drift at your endpoint. Right, approximate your target distribution at the endpoint. So this is actually not something you would want to do. And here's another motivation. I think I'll just go over this briefly. So another connection between optimal control and Langevin diffusions or gradient-based methods is something called a Turnpike theorem. And this occurs a lot, for example, in economics, in planning. So very briefly, generically stated is that most of your optimal control trajectory is actually not that complicated, and it's spent near equilibrium states, except for a short period at the beginning and a short period at the end. And the reason this is valuable is that that means that when solving the static problem, let you approximately solve the dynamic problem. And obviously that's a lot easier. And this requires a distributive system, which I'll cross over. And one very interesting result completely is this work on the long-term behavior of entropic interpolations. So the long-term behavior of entropic interpolations behaves like this, where also restricted to is the Schrodinger bridge solution, and PT, sorry, is the gradient flow. And this thing to note about this bound is that it's for all, this constant C on the outside depends on its finite time interval from 0 to 2. But this holds for all three. And this is actually, this actually is the worst case possible for convex objectives. That you can often do better, such as 1 over t. And why this is interesting is that it tells us that for large enough time horizons, the observation at some time scale little t is almost independent of the observation at some much later time. So the entropic interpolation is basically the gradient flow. You're dissipating entropy as you expand your time horizon. Okay, so now that we've discussed optimal control and how they're different from gradient methods, we can maybe think about when they might actually overlap. And importantly, we should only hope for this in convex settings, because in non-convex settings, if you think about it, well, we have a finite time horizon for the control problem, but for Langevin and for a non-convex objective, all we know is that, well, structural gap will tell us that we will have to wait exponentially long in dimension in order to convey in terms of optimization and sampling. But that convergence is, well, first of all, you might not know, I probably don't know a priori how many modes of that non-log concave distribution you have. So how do you know how long you should have your time horizon for your control problem? And the other thing is that, well, you will spend an exponentially distributed amount of time, randomly distributed amount of time within each basin of attraction of a local minimizer. So you basically have a sum of exponentially distributed times within close to minimizers, or who knows how many minimizers you have. So it's hard to even specify a time horizon for a control problem that you could compare to the Langevin diffusion in the non-convex case. But suppose we just restrict ourselves to the convex case, then question is, well, is there a gradient flow that corresponds exactly to an optimal control, and what would that look like? So if you actually write out what we would need from such a thing, like in a deterministic case, you have to have that your control, at the very least, enables you to factor out any time dependence, in which case you would do reparameterize time, but that's kind of not a very interesting exercise. So if we simplify, we want to say that, well, the optimal control is just completely independent of time, and we have the objective FB from conservative vector field, so the negative gradient of shift. And here to think about this problem, we will start with an infinite horizon control problem. And Here we actually do not have discounting, which is not always the case with infinite horizon problems. For example, again, in economics, we have problems that involve depreciation of machinery, interest rates, and so on. And there will be a discount factor within the integral here, but we're not bothering with that. Okay, so we have a candidate cost function that might look very strange. It is composed of functions f and g and their duals. And we require that, importantly, that f and phi are so convex and going to infinity. So one tool from optimal control that is very helpful is so-called verification theorem. So if we have an ancestor hypothesis for what the solution is, then assuming sufficient regularity of it, then it is the solution. So sufficient condition, basically. So we have our ansatz that this is a Bregman divergence given as such. We can check that this candidate optimal control is independent of the time, which we've required above. And then by Ventral-Young inequality, we have that this inequality is attained if and only if the control used is this gradient of f of the mirror map. So this is the function, and the axis control cost is given as such. And if you look at it, it should look like there is a Bregman divergence. So we push around the term sum, axis control cost. We can recall that the central biconjugate of a convex function is the function itself. Push around the term, and sure enough, we find that this control problem is basically minimizing a convex distance-like function, or the Bregman divergence. And it's important to verify that this thing actually function value decreases over time, because we want this for optimization and our control problem. This is not hard to like, this is kind of very fundamental for the deterministic case. It gets a little more complicated for the stochastic case. So this cost function before looks very strange, probably. And I mean, to be honest, I still think it's kind of strange, but one way to think about it is that the finite time problem, the total cost function corresponds to the action. An action of functional composes of a self-dual Lagrangian pair, which is defined this way. So one Lagrangian corresponds to the running cost, and the Lagrangian corresponds to the sum of the initial and final states. And we need both so that our initial value problem actually has a solution, because otherwise the gradient flow corresponding to the control might not exist. And I think the best way to think about this is, even if it is very weird looking, optimality with things involving tensor conjugates occurs at subdifferentials. So for differentials, gradient flow. Another interpretation is that the time reverse dynamics, so if we go backwards using the negative of the optimal of the control, we have a distributive system. And that is one where we have a so-called supply rate that is going to exclude the storage function. So you will be putting into your system more than the system can store. And the storage function in our case is our only optimal function for the primary system. And with equality, so no ways we have supply exactly the storage if and only if we use the optimal control. And one way to think about it is that means that we're transferring material relative to the geometry induced by the distance generating function. Or the geometry given by the gradient. I think I've been going pretty fast, so if anything I said was kind of weird and deserves clarification, ask. Okay, so no questions. Okay, so a little bit more on what the system is. Well, I was telling us is that the mirror descent dynamics given with us is a primal version and a dual version corresponds to an optimal closed loop stabilizing control. And the value function B here is a optimal function for the control dynamics. And sorry, I think I messed up my notation. That should be X subscript infinity is globally asymptotically stable. And if we this thing, you can check that it is regionally unbounded, which is necessary for to have bounded level sets everywhere. And moreover, it is strictly decreasing for all time. So we have an invariant set that is unique and a single point with global asymptotic stability. And this just offers another perspective optimization, which is that if the function f is strongly convex, then we have exponential convergence to globally asymptotic stability. This sort of control theoretic way of framing optimization. Okay, so here's a very trivial example. So we have an ordinary least squares objective function with full rank matrix A. So cost function looks like this, and it's defined relative to this thing y bar, which is just the overall relation. The control theoretic interpretation of this is just that the gradient flow is basically optimal control for this infinite horizon problem of stabilizing this very boring linear system with a quadratic control cost and also with a very boring geometry of the mirror map being completely identity over here. Okay, so I think this is what everyone signed up for, the stochastic case of this. So as before, we had the gradient flow, but now we're making it a diffusion process. So we have the control that in the place of the diffusion, the drift term, and then our diffusion coefficient is this thing. So instead of your standard Langevin diffusion, we just have identity scaled by temperature. We have where we have the tunable parameter epsilon and this positive different matrix given by sigma. And for this diffusion process, we have a optical function. And here this is going to be finite for the application because it's stochastic. Where the terminal cost that is a Bregman divergence. Okay, it has a value function. I think it is going to satisfy an HJB equation where now we have the generator of value function. So we have an additional second order term that we did not have before in the linear case. And that will actually explain why we have a finite problem and that the length of the horizon will come into play. So then we have solution, which looks much like the solution in the deterministic case. We have this cost function that looks weird and is composed of f and p and conjugates. Then we can verify that this thing solves the HGB equation and therefore is the solution. So first of all, again, the optimal control. The value function is not independent of time, but the optimal control, which is the gradient of the value function, is indeed independent of time, as we require. And then we can check that this inequality always holds, and it's holds with equality if we use the optimal control given as follows, and that follows again by the French-Young inequality. So again, we have this time dependence of the value function on the horizon from this would be generator of the value function. And so, yeah, so that's one of the comes from the tunable parameter in the diffusion coefficient. Okay, so what is interesting is I'm kind of leading up to is that the optimal control yields neural Langevin dynamics, and there are actually experts on this topic in the audience. So neural Langevin dynamics are specified like this. And for a solution to exist, we actually need something that is called the a modified self-concordance property, which relates the Hessian of the distance generating function to its gradients. That's kind of, I mean, it's kind of a dodgy proposition sometimes because even if alpha is greater than 0, you can think of many sorts of mirror maps where it can be arbitrarily broad, and we don't want that for our diffusion process. So I didn't write it here, but this thing is analogously to the ring flow has a primal version. And it was just calculus. Not even calculus, it's just algebra. So if you're looking, we say about this process, if f is convex but not strongly so, then we can talk about the expected average objective over time. And in fact, it decreases as 1/2. And here's Bregman divergence term, and with an additive penalty that, not penalty, just an additive term that depends on dimension and your tunable parameter epsilon. And I guess you can kind of think about it, you know, with each into temperature. So if this epsilon times dimension term is small, then the neural Langevin dynamics behaves very similar to the regular mirror flow, which is not surprising. You can think about this in case of the vanilla Langevin diffusion. Your inverse temperature contributes trivially, then you basically have gradient flow again. And this theorem basically captures what I just said a little more quantitatively. So for epsilon exponentially small, then with high probability, over the entire time horizon, the worst case difference between function value of the neural Langevin diffusion and the mirror flow is as such. It's not a very exciting result to prove. It mostly comes from Lipschitzness and bounding the behavior of Brownian motion over analogue.
Belinda, can I just clarify? So what is y infinity?
Oh, that is the terminal value of the dual variable. That's regular y and infinity. So y infinity is dual of x infinity.
But does that mean you run mirror Langevin diffusion like fixing constraining endpoints?
No. It's just what you will obtain with the optimum control.
Say this again.
Is what you'll obtain using the optimum control. So x, so the equilibrium that we obtained here, for example, so that's just the dual version of the equilibrium attained with the optimum control, and likewise that is the equilibrium attained with optimum control for the mirror flow.
Okay.
So, okay, this is actually just kind of like overview of other people's work. So what, yeah, I think like surprisingly to me a little bit, there apparently wasn't that much talk on mirror Langevin diffusions earlier in the program, which I think is kind of a pity because it's very cool. So, I mean, I think it's not hard to see that mirror Langevin diffusions are, strictly speaking, like the more general case of the vanilla Langevin diffusion, because you can just take the distant generative function to be identity, sorry, the mirror map to be identity, and then this Hessian goes away and we walk with an isotropic Gaussian in the discretized case, or a standard Brownian motion in your diffusion term. So what can you say about this thing? It has good convergence guarantees.
At this point, I have to ask, right? So you have this, I guess you pronounce psi, how do you pronounce the Greek language? The Greek language psi, but in English.
Well,
What is the pronunciation?
I'll
One is psi, one is psi, one is psi.
I mean, I think I should always defer to Greek people on this. So, okay,
And not for the record, but
okay.
communicating here, I'd like to figure what is the consensus, you know, I see size and size.
So it's the other one. The other one's
Okay, so
Yeah.
this is the conjugate of psi, you take the inverse of that. You take the Hessian of that, and you would like this to be split. I don't know how to buy
right,
it.
right.
So now the $1 million section, how is it doing that? The Hessian of the conjugate on the inverse of conjugate.
Oh, so actually, I mean, in general, we punt on this because either you choose the mirror map or it's inherent to the problem. I mean,
You have the same. Let me see one example where I can set this psi, whatever, and then they conjugate the inverse, the Hessian, solar ellipses. We have such a, let's say,
so we require psi to be the genre, so strictly convex, and so it will be like this Hessian will be strictly positive, it will be positive definite, but how much though, like what is that smallest eigenvalue? It can be arbitrarily bad, that is absolutely fair. For example, I mean, one very natural mirror, not mirror, right, is in soft constraint optimization, where if you want to constrain your iterates to be within some polytope, like x less than equal to b, then we can use a log barrier function, and it's very effective, but and the log barrier function corresponding to the mirror map corresponding to the log barrier function. That, well, depending on where you are within that, relative to that polytope, yeah, absolutely, like, these quantities will not be there. So that's, yeah, that's ranging. So we usually have our choice of mirror map, but like what it does, like, and actually this choice of mirror map is everything. So I mean, this bound, if you look at it, well, it looks similar to the bound for the vanilla Langevin diffusion, except that importantly in the exponent we have so-called mirror Poincare constant, which is your regular Poincare constant, but relative to, instead of the Euclidean geometry, the geometry induced by the mirror. So if that quantity is not nice, well, it's in the exponent. So life is not going to be necessarily good. And the other interesting thing about this bound is the use of the asteroid divergence, which is maybe better than your standard KL, but why that is, like, I actually don't know sort of the deep philosophical underpinnings of that. So if anyone wants to enlighten me, feel free. And of course, we're like, what is this thing even sampling from, right? This low stationary distribution is just the push forward of the result with F relative to its own mirror.
But from a computational point of view, I don't understand because you're right, it's the main message is that use this kind of dynamics, right? So then I have to design this C, you okay? I have to find the conjugate of that. Right?
Yes.
And I think the LCM, but I'm already defined by the and then somehow you have this in an explicit form and usage. That's why I'm wondering what is the typical paradigm here? I mean, from where is I don't know, probably from the but usually for me, it's this example, this is the message that okay, you can design this kind of function. You have a typical paradigm or is it a little bit of calculation?
I mean, my personal favorite example, and just borrowing straight from the discrete deterministic case, is mirror descent constrained to be within some specific polytope. And in that case, like, you really, like, there aren't that many, like, you could choose a mirror map, but like you probably don't want anything different from a log barrier function, which is really hard to like get beyond that polytope. And yeah, the mirror map is like, I'll talk about this whole thing, but like the mirror map, whether it's your choice or just almost like given to you by the requirements of the problem, it can be not so great, and that will affect you everywhere, including in the analysis of this discretization. So yeah, this is the standard discretization or discretization. You can have it in primal space or dual space, and it converges. Like that we know from the other years that we know in general. We have to like wait until the other years, like everyone knows that it's biased, but it converges to the diffusion as the step size goes to 0, and it's comparable in the case of the Langevin diffusion. And therefore it's good for sampling with a pretty good mixing time, but there are some caveats within this result. that are sort of non-artifact of the analysis for the fact that the mirror map can be allocated. Okay, so I thought I had a footnote on this quantity. But I didn't have to, but yes, I did. This is the original footnote on this self-concordance like property of the mirror map. So this parameter alpha actually finds itself into this note here. This parameter finds itself into all of these. So, for example, the maximum step size that you can use for your discretization for to work at all will depend on alpha, and in general, it is everywhere, and it is a consequence of the mirror map that you really cannot escape. Okay, so just some notes instead of sampling on optimization. I think it's harder to understand optimization and control together in this case because, right, like, what are we really optimizing? Are we optimizing like F in the standard optimization setting, or are we optimizing our control cost? But regardless, so in the deterministic case, we're guaranteed a functionality decrease. But in the stochastic case, we do not necessarily have that, even in expectation. And what we need to do to have it is to use this tunable parameter epsilon. So which is on this quantity where we have epsilon times some stuff that we don't really care about, and we choose epsilon appropriately, then indeed we will have function value decrease. And sort of semantically, like, what is epsilon? Or what is it give us? What is the degree of freedom? So the value function is, sorry, it was typo, but first term should be a Bregman divergence. In any case, the value function is Bregman divergence with this additive term that includes the length of the time horizon, F1 and dimension, and F1 goes to 0, obviously. For typos, we recover the value function for the deterministic problem. But then what does that do? Well, that comes at the cost of efficiency and sampling, because then if we scale that down, then we will suffer in terms of our parameter alpha, which again reflects all parts of the discretization analysis, and therefore this quantity will be Wasserstein cube. Oh, the Wasserstein, but again, like this mirror map will really affect everything. So instead of vanilla Wasserstein cube, this is Wasserstein with relative to the push forwards induced by the mirror map. So Wasserstein between where you currently are in your discretization and Gibbs is given as such. So again, this self-concordance like parameter alpha ends up literally everywhere. Again, I don't think it's an artifact of the analysis. Maybe things can be improved, but you're not going to get rid of this dependence everywhere, I believe. And control theoretic interpretation of this is simply trading off between optimizing the control cost and a faster mission time. And of course, can go in multiple directions. For example, I mean, we need, obviously, for the primal-dual pair, we need that the mirror map is bijective. And therefore, the distance related function is works, but we don't know convex. Again, something we want to use. We talk about local, visible optimization, what that means. In both areas. We'll come to that now. Not just resort methods, but what it's technology methods, like momentum methods, whatever. I think that's all I have.
Any questions?
Very nice talk. If I understand well, all your results, the sampling problem, depend on having a Poincare constant with respect to the new metric that is induced by psi, right?
So what was the thing about a constant? You mean the parameter alpha?
Can I? So, yeah. Okay, okay. Probably I have to look at it better. But I thought these results make use of some property, no? That you have a kind of Poincare constant with respect to the new metric, but probably not.
Sorry, what?
Leave it, leave it. I'll ask you later.
I mean, it's possible I have typos in here, I'm sorry.
Yeah, okay.
Any other questions?
I'm curious, you know, the stuff that like Elad, Sham, and others were doing for like the non-stochastic version for just a normal kind of control problem, but just like LQR, like linear quadratic regulators. Like, do you have, basically the thing is you trade, I guess, expected cost for some notion of regret. You know, if there's somehow like some analogs that you can play this game as well in this kind of distributional setting where you kind of have some like online sort of style setting where there's worst case errors potentially, but then you trade off like expected cost to go or something by some notion of regret, meaning like you're just competing with the best controller in some class.
That's a very interesting question. I think the distributional case is very interesting, but I think in terms of regret, I think even though we have cost to go function, like sort of the online setting, like what are you paying at each step is hard to think about.
Oh, there's a sneaky, like, you know, reason why I'm asking this, which is like you could imagine these sort of like non-stochastic settings could be useful if, for instance, you have some way to estimate something like a cost to go function. If somebody hands you a score, for instance, from like a pre-trained model, then you could try to estimate kind of the cost to go, which is like how long do you need to until you finish the, you know, like the diffusion to something close to convergence. But that's not like a stochastic error. It's some kind of like worst case error. And then you could try to sort of like use the pre-trained model on top of some controller to get a faster algorithm.
Yeah, that's actually, yeah, that's a very cool motivation for the question. And I'll have to think about it. It actually makes me think on a diffusions, but of flow matching in terms of just like estimating some cost to go quantity from data or whatever. Yeah.
Thank you.
Okay, Belinda, thank you so much again for this excellent work talk. It's very interesting. And that's why I try to learn a little bit and understand. So let me do the steps. So you have the dynamics, and then this again, C star for you is the dual. This is the language you use, the dual of your.
Yeah, so the mirror math is free and has dual sheets are only. I mean, depending on whether we want to work with the, sorry, I don't have the, I guess I never wrote out the dual FD, but yeah, so
Yeah,
I wrote up the stochastic version of X, right, and whereas the stochastic version of.
that's okay, because I mentioned earlier conjugate, I want to say dual, right? So
But let's go back to the SDs and then to the numerical scheme. This is the most important thing for me. Okay, so you start with a dynamical system, and then of course you write all the discretization, and the problem is you may exit from your domain, right? And then that's why you apply there the gradient of C star. Is that correct?
I mean, I think that is the most, that is-
Sensible thing to do.
I mean, the mirror map can be many things, but I think like my favorite example of mirror map is constrained optimization.
Yeah. So that's why you apply, right? Because the worry is with the Euler scheme, you will escape. Do you understand correctly? Because I try to match now your notation, and I try to understand what is happening, because if I see now in the Euler discretization, probably it's a misprint, but maybe I'm wrong because I don't know. In the diffusion coefficient, you don't have the inverse of C star. You have only C star. Is there a misprint from the continuous dynamics, or there is some... Do you see in the diffusion coefficient? Now your C star is not to the -1. You don't have the inverse.
Oh, sorry, one of them should be regular C, not its dual. I think.
Yes. Again, try to see how the Euler scheme is written. So from the dynamics, you write the Euler scheme, and then you apply the gradient of C star, right? So I will expect to see the same diffusion coefficient as in the continuous time system. Is that correct?
Oh, I see what you're
Because in the continuous time system, in the diffusion coefficient, you have C star -1, the inverse, I guess. Is that correct? So I will expect to see this in the Euler discretization, or am I missing something?
Yeah, that's a typo.
That's a type. Okay, that's okay. And then this epsilon also disappears. And I try to understand why.
Oh, it just becomes the step size.
It's absorbed in the step size. Okay. All right. Okay. So then maybe I have a clear now picture. So that was a typo. And then this is how we apply the Euler scheme. And then the interesting thing is the equivalent formulation now. Okay. And this is also interesting, I guess. And we have been asked to say a little bit of the calculations, but we don't have the time. So maybe we discuss later today that the equivalent formulation also for you is guaranteed that it stays in the domain. Is that correct? Because in some sense,
So log barrier function is not hard, like a hard constraint, but it will make it like, extremely hard to exit.
but do you have some small probability that you jump away? Because
Well-
I see you multiply with ZK, right? Which is a Gaussian random variable with very small probability, can take very big values and then push the value of your YK, your approximation, to be outside your domain. But there you say equivalently, and I try to understand in what sense equivalently. I guess this is my question.
Yeah, actually, I mean, I didn't actually specify an example here about, but if I wanted to specify a certain polytope constraint, and you give me your inverse temperature of your Brownian motion, then yeah, we could actually write down all of these things and obtain like actual quantities.
Okay, so we are slightly over time. So let's thank the speaker again.